picking this up. Okay, chemistry time. Chemistry time. Today we would talk about the SI, but I have a little addendum here. But what we are going to talk about is unit conversions, briefly, and significant figures. And error. Unit conversions briefly, significant figures, and error. The first thing you need to know about is something called the SI, which is one of your vocab words. It stands for, it's French, it stands for the système. Oops, if anyone can smell anything, right? Système. I think the accent is on that boy. International d'unité, which is French for the International System of Units. We call it the SI, even though it's abbreviated in French for this, and we call it, when we unabbreviate, we call it the International System. This is like the new metric system. And that reminds me that I gave this speak that I'm giving you, that I would give you. I just told the freshmen about this yesterday over the course of about 25 minutes. In order to have more time for these other things, I'm going to encourage you to watch that video so you can better understand the SI. But for two reasons, we're not going to talk about it again. One, because we did talk about this in physical science either last year or the year before. And so you should remember it from then. And because that information is available. Everything I would say right now over the next 25 minutes is available for you to watch that I had said this morning over 25 minutes. So there's a video called the SI or something like that, -physical science. And that is what I would encourage you to watch if you have questions about this. Furthermore, as a third point, the information that you will need is all in your book. So if you read your book and you remember from last year, and you watch the video to pick up any information that you may have missed, that is the video that I gave to the physical science kids this morning, you should have a full understanding of this. Do you have questions? I usually don't like to do that, but in order to save time, that's the way it's going to be, and because it's review. Question? SI.
No, down.
Metric. It is like the metric system. The metric system was invented in the late 1700s in France, and this is like an improved version of that, in that it contains all the quantities, all the units that we need to measure any quantity physically in the universe, as far as we know. There are 7 base units. Your book talks about that. The video talks about that. You should remember them. And there are also prefixes to not just know, but have memorized what the prefixes stand for. So if I say kilo something, what does that mean? 1,000 times. So if I have a kilosecond, a unit we don't use very much, but a kilosecond is 1,000 seconds. A kilogram is 1,000 grams, etc. So those kind of things you need to know. That's all we're going to talk about from Unit 1, except there's also this idea of density. You need to have, this is the chapter in which we talk about the equations for density and volume. Coincidentally, also in the physical science video this morning, but I want to point out that I like to use the Greek letter rho for density, where rho is density, usually measured in grams per milliliter. Kilograms per cubic meter is the actual SI units for this, but this is more common. Also, grams per cubic centimeter means the exact same thing, literally the exact same thing. Milliliters and cubic centimeters are equivalent. M is mass, measured in grams, and capital V is volume, measured in milliliters. For this one, capital V is volume, L is length. What do we use in the SI to measure length? What unit do we use in the SI to measure length? Meters. Meters would be the base unit. W is width, also measured in meters since it's a distance unit. H is height, also measured in meters since it's a distance unit. And then, just like we had talked about this before, but just like in algebra, x times x times x is x cubed, meters times meters times meters is meters cubed, or we usually say cubic meters. Both of these you're familiar with. These are not new, right? I pointed them out because these are the math for this chapter. It's not the only math for this chapter, but these are the equation-based math for this chapter. Both of these are brand new to you, yes or no? No, these are both entirely review. You should be completely familiar with them. I just point them out so that you have them so that you can study more appropriately. Lesson 1 of your chapter also goes in depth about how to measure rectangular prism or other regular volume, and how to measure irregular volume, and how to measure temperature. All of those things you should read and know about, but you have known those before. They're also review. So let's move on to another thing that is review, and that is what I call in physical science unit conversions, but what your book and what is more appropriately called dimensional analysis. So I'm going to erase unit conversion up there, change it to dimensional analysis, and you should write down dimensional analysis. That's the next section here. Unit conversions is not wrong. It's just more accurate to call it dimensional analysis. What does that mean that we're going to be doing? What's it mean to analyze? Analyzing the dimensions. What does analyze mean? Yeah, to study, observe, to, in this case we're going to do some math with, but we're going to be trying to get a better understanding of the dimensions, here being a substitute word for unit, well, the ways of measuring things that we use to measure. And I'm not going to go through the steps like I would if you were a freshman because we already know them. Instead, we're going to do an example. So the example is we're going to convert 673 yards to meters. You don't have to write this down. A lot of people get confused and think that this is step 1. And this is a little format that I think, as far as I know, I made up. I might be remembering it from when I was in high school. But this little 1 unit and its number, arrow, another unit, as far as I know, I made that up. So this is not step 1. This is not step 1. This is not step 1. What is step 1?
Write down the equation.
Not in this. What is step 1? Right, I heard someone say it even today. What do I do for step 1? What's the first thing I need to do for a dimensional analysis problem? A unit conversion problem. Right, yeah, you know what to write, but what do we call that? This number is or this value is the
volume will change. My head keeps going. Conversion unit. My head keeps going.
Given. Yeah, it has a G like origin is what you probably remember, but it's given. So we write down the given. You need to do that. Conversion bar is step 2. I went ahead and did that while we were waiting for what the name of the first thing was. Write the given, write the conversion bar. And then we're going from yards to, but this is where, and I use terminology like this, yards to, because see here, think about it algebraically. If we have yards in the numerator here, which this is mathematically equivalent to this, is it not? Yeah, so that's fine. It just shows us that that is in the numerator. So I have yards in the numerator here. To eliminate the unit, just like this algebraically is 1, yards divided by yards is 1, which effectively means, and we don't say in math, Mr. Stanley does not like when you say this, they don't cancel out, although that's an easy way to think about it. They don't cancel out, they reduce to 1. And if we have 673, so now instead of having 673 yards, we have 673 yards over yards. 673, the yards reduce to 1, don't they? So it's the same as this. And now we don't have any yards anymore, we just have 673. So that's why we sometimes think about them as canceling out. That's not the correct terminology and doesn't really show us what's actually happening, but that is what's occurring when we divide something in the numerator by that same thing in the denominator. So in that way we can get yards to reduce to 1 in our equation. What would be a good thing, another unit to go to? And when I say go to, I mean what do we want to convert this yards into? Meters would be great, wouldn't it? Do you know how many yards are in a meter? Nope, neither do I. Are you going to know on your test? No. Sometimes you'll be given something that'll say on the top like 2.2 pounds equals 1 kilogram in weight. You won't always be given that. And since you weren't given how many yards are in a meter, you can't assume that you should know that. What do you know? How could we get from yards to meters with what you do know? Okay, so yards to feet, right? And then we're going to reduce out feet to inches, and then inches to centimeters, and centimeters to... And for this, the only one that you wouldn't have already known, the only one you would have ever had to learn in the last 4 years is this one. And what is it? And you should have this memorized. 2.54 centimeters in an inch. And the other reason we use this is because this is an exact value. This, we could go we could go feet to meters. 3.28 feet equals 1 meter. But this is not exact. Let me say that again. Not exact. This is only good for if we have 3 significant figures or fewer. Whereas this is 2.54 is exact, at least 5 significant figures. So we want to use this where we can, because then if our given had more significant figures, which we'll talk about in a second, but if our given had more significant figures, this would reduce the precision of our answer, where this would not. Does that kind of make sense? We'll talk a little bit more about that when we talk about significant figures, and remind me if I don't talk about it. But this is not exact, so we don't really want to use that. The best one to use is this for length and for volume, if we're using regular volume. Let's go through. And by the way, this is the order I like to see people do them in. Given, conversion bar, units, and then values. People are trying to go along and put in values with their units as they go. I don't prefer to see that. I prefer to see units, and even, this is kind of like nitpicking and I can't control how you think, but I like you to think about it the way I said. Yards to feet, feet to inches. It just helps you, I shouldn't say that. It helps me with the bookkeeping in my brain to know where I'm going next. And I think it would help you too if you would give it a chance. So let's go through and put the values in. 3 feet in 1 yard? Yeah, let's say it mathematically. What operation does this? This represents division here, but these two things are what? Why am I able to just do this? How come it's not ruining it mathematically for me to multiply this by 3? They're equal. Yeah. Look, this, please write this down somewhere. This is why we can do this. I drew a little like grave with the tombstone on it, but that's not what I meant to draw. The reason we can do this is because effectively, what are we multiplying it by here? If we multiply it by 3 feet over 1 yard, the same thing as multiplying it by what number? No? 1. This thing here, 3 feet divided by 1 yard is equal to 1, because these two things are equal. So if x equals y, right, and x divided by y equals 1. That's why we can do this. That's why it's mathematically sound to do dimensional analysis, because we're just multiplying by 1 numerically. Right? The number itself is going to change because we have units with it, but it's numerically equal to just multiplying by 1 by 1 by 1 by 1. We're not changing the value of this. Put another way, if I measured the actual length of this keyboard, saying that this keyboard is, hold on, let me do this right. Saying this keyboard is, very close, Peyton, 15 1/8 of an inch, is the same thing, numerically the same thing as saying that it is 38.81 centimeters. They mean the same thing. They're different numbers, but they have the same meaning. They have the same real physical, real world meaning. That's why we're able to do this. It just helps us so we can change what unit. That's why in physical science we call it unit conversions. We're only changing the unit. This value is going to mean the same thing as whatever we get over here. These two things are equal because each of these is equal, which means we're just multiplying it by 1. Does the theory of dimensional analysis make sense? We're analyzing the dimensions. We're thinking about the dimensions that it's measured in and changing them from one to another. Let's go on to the next way. So thinking about that, let's phrase this one better. I don't want to hear that. I want to hear, 12 inches equals 1 foot. 2.54 centimeters equals 1 inch, and 1 meter is equal to 100 centimeters.
So it's 615.3912 meters.
What? Say the whole thing. Let's hear the whole thing.
3912 meters. That's it.
What's the trouble with this? What's the clear trouble with this?
It's too long.
No, that's not a real bad trouble. Like it's obviously it's more than we wish we had to write. But what does this mean? When you see this is the same. We talked about this in the measurement. You're getting closer. This means when you see this number, this means that this has been measured. This is what we call artificial. Write this down, please. Precision. Artificial precision. Doing this math and writing it this way tells the viewer, the observer, I don't know, whoever's reading your data, tells them that you measured this quantity to the, what is this spot? Well, let's go over clear here. What spot is this? What's in this spot? Hundreds.
Tens, ones, tens, hundreds, thousands, 100,000.
So this tells your viewer, whoever's reading your paper or whatever, that you measured it to the 10,000th of a meter. Now let's look at the meter stick. 1,000th of a meter is 1 millimeter. That's this little baby here. And so then a tenth of that, one of my fingernails is wider than the amount we would have measured this to. What were we actually given? What is this accurate to? This is precise to the nearest what? Yeah. So if we actually measured it as this, we rounded it up to this. If it was this, we rounded it down to this. So anywhere between these two things, yards, anywhere between these two could have been the actual value, but I don't know because the precision is only to the nearest yard. So when I measure this to the nearest 10,000th of a meter, that's artificial precision. That's telling the viewer or the reader that I measured it to this amount. Did I actually measure it to this amount? No. What was the nearest thing? Yard. So what should this be?
Just
615 meters. Not because it's easier to write, not because it's easier for me to grade, but because this is how precise the given was. Now before you ask your question, right, and I'm going to address you in a second, but let's write this in big letters over here. The solution, I was trying to think of the right word for answer. The solution can only be as, what was the word? What's that? Precise. In great big old railroad graffiti letters. Yeah. As the given. Why?
Because the given is not that precise.
Yeah, but you're just saying the same thing again. Why can it not be any more precise?
Because we don't know if it was higher than 73.
We don't know for sure because in this case, it was given to us by a problem that I made up. But this would have been a what? If we were actually using this for some observation, this would have been measured. Someone measured it to the nearest yard, and so when we convert it, we can't pretend like they measured it to the nearest 10,000th of a meter. So we can only have as precise, and that's not the flip side of this, but another aspect of this, a corollary to this, is that we should always try and be as precise in our measurements as we can, so that when we go to change them, if we do, they're useful for that, right? This little principle here, I'm going to get to you in one second. This is the principle of significant figures. What's your question?
So if it actually was 673 yards, would you have to put 673.000?
Yep, 673.000 yards.
Okay.
What if we were chaotically, or in shop class, which is kind of like chaotically, what if we were chaotically using things like, what if I had measured it as this? 673 yards, 11, no, that wouldn't quite work. Yeah, it would. 11 inches. No, let's do this one. 1 foot, 3 inches, 3 and 15 30-seconds of an inch. What if I had this? This is precise, isn't it? I mean, like I said, it's chaotic. This is a lot of numbers and symbols for a pretty simple answer. But if I had actually measured that, this is precise. What I'm illustrating here, to the 30 seconds, yeah. So this is precise to the 100th spot, probably, maybe even the 1,000th spot. But do you see another inherent problem with this kind of measurement with the English system that is resolved by I had it written over here, the System International de Unités, the SI, solves the problem of how precise is this? Because, there is obviously more precision than just this.
It's as precise as to your 30-second.
Yeah, to the 32nd, which is a fraction. So, and then also, but 32nd of an inch, which is another fraction of a yard. So having this chaotic system where we use 3 different units and one of them is some crazy fractions is it's not useful for this kind of math. And when I say this kind of math, it is useful for if you're only using this system and you're building a whole house and you want them all to be this precise, but you're only using this system. I guess that's fine. It's still a little bit unwieldy. It's not fine for if everyone else is used to talking about things like this, like, the cubic capacity of this aquarium is 70,418.3 cubic meters, and you come in talking about cubic yards, cubic feet, and cubic inches, that throws everything off. Do you see? Like, since everyone else in the world agrees to use this, which is, by the way, mathematically simple, because it's decimals, everything's just dividing by 10 or 100 or 1,000 or whatever, and you come in with this, it makes things hard. It makes it difficult to get accurate, not only precise, and I do mean accurate here, because this may not have the accuracy of this. It might, but it doesn't necessarily have to.
So when I said it's not as accurate as SI,
No, but it can be. Just, well, which of these is more, not even just accurate, we're talking about precision here. Which of these is more precise? Let's do 12 meters and 13, these are not divided, I don't know. We're going to have two different values here. 12 meters and 13 feet, 11 and 3/4 of an inch. Which of these is more precise? No. This is more precise. Yeah, I'm not saying the SI is always more precise, and we certainly can't say which one's more accurate because we don't know what they're measuring. Remember, accuracy is how close it is to the accepted value. So this could be more precise. It certainly could be. But this is easier to do math with. And this, since this has two different units, and if we include yards like that other one did, has 3 different units, it makes it really unwieldy to do this process with. Basically, this is a relic of the past. There is a better way to do it, and it is the SI. The SI has better measurements. It's easier mathematically. It's easier to measure because instead of having, I'm positive that Mr. Jones is very good at this. Like, take out the tape measure. I know what each of these little increments mean. I'm positive he's good at that because he's been doing it his whole life. But if I have these two, and there are 10 of them here, Asher is 2 years old, and he can count to 10. Anyone, if it's right here, can find that it's 2.1, 2, 3, 4, 5. Anyone can do that. 2.45 is this. Whereas it does take some learning. You have to get good at this. That's another way. So it may be more precise to use this sometimes, depending on what tools you have available. But this is an easier system to use for mathematically, for measuring, just for the units themselves. It's better in a lot of ways. Do you have questions about how unit conversions work? Let's do one more example. I've really made a mess of this board. This looks like a crazy person did it. This looks like a crazy person did it. Put in the comments how I could have organized this better. Comments are disabled for this video, so good luck. Let's do one like this. What if I had, speaking of my aquarium, what if I have the great white sharks at the Denver Aquarium are swimming in a 70,412, whatever I had said, 0.3 liter aquarium. Let's call it, instead, to suit my purposes, but let's call it cubic meters. That's not the same thing. Liters and cubic meters are not the same thing. I just changed it because I want a different example. But I want to find out how many, for some reason, because I love big numbers, I want to find out how many cubic centimeters that is, okay? Are you with me so far? Is there parity here? Can we do this? Yes. They're both volume measurements. We can do it. Step 1, 70,412.3 cubic meters. Answer his question. Can you just divide it by 100? Can you just divide it by 100? Why not? Well, yeah, let's look at this. For one thing, I want to see your work, yes. But let's look at this. What do we want to get rid of? That's colloquial. What I mean is, what should we reduce to 1? Meters. 2?
1 over, or 100.
Shh, no, not yet.
1 meter.
That's not the next step. What am I going to? Centimeters. Okay. Now what are the values that go in here? Say to yourself. Say it. We'll say it out loud now also.
100 centimeters are equal to 1.
Yeah. Okay, let's try it out. See what we got. 70,000 times 100, we're going to get 7 million. I know, that's what I'm doing. But now let's look actually very carefully at our units. Let's do this as a math problem. That's what we have, right? Just the units. There are no numbers here, just the units. That's what we have. Do we all agree that's if we get rid of all the numbers, that's what we have in here. Now let's solve this. What do we actually get? Let's simplify this expression.
Oh, like to scientific notation.
No, just simplify this expression in algebra. You've all taken algebra. Simplify this expression.
Take the cube away. Oh, you gotta take the cube away, like cubing, or not cubing.
No. I'm not asking you to FOIL or anything. Just simplify this.
M times centimeters, or divided by centimeters. Right? Or there's another M that's there. There's 4 times.
Let me help you there. That makes it a little easier. Now do it. Okay, let's do the next. Let's simplify it one step at a time. Next one is meters cubed centimeters, right? Over meter. Now we can reduce those, so now we end up with meters squared centimeters. Is that what we wanted? No. Do you see the problem with what had been suggested?
Yes.
Okay, so what do we have to do instead? So that's not good enough.
What the science teacher says.
No. Well, yeah, but that's not what I'm
Let's get
getting
rid
at.
of the cube.
Yeah, so how do we do that? We have m times m times m here. So
Cube at meters cubed. We have to cube them both. Yeah.
is this still true? Is each of these equal to 1? 100 centimeters is equal to 1 meter. Is each of these true? Is it going to change the value of this expression here? No, because we're just multiplying by 1. But it is going to change it numerically. Now look what happens. Instead of having this mess, let's do the same thing. I'm going to show you what we have. We have meters cubed. We're multiplying it by centimeters and dividing by meters. We're multiplying it by centimeters and dividing by meters. And we're doing that again. Now what do we end up with? Simplify this expression.
Billions.
Just the units.
Oh, centimeters cubed.
Yeah, we end up with centimeters cubed. These reduce to 1, and we're left with centimeters times centimeters times centimeters, which is cubic centimeters. Is that what we wanted? Yeah, it is. Yeah, the number I don't really care about that much. I'm sure it is. Let's move the decimal place. 1, 2, 3, 4, 5, 6. So
70,412,300,000.
yep, 70,412,300,000 cubic centimeters. The number here is not super important, but do you see what I mean? I hope someone wrote this down. This step where to do dimensional analysis on a quantity with an exponent, we do that same thing however many there is. Let's do another example of that real quick.
Don't erase that one just yet.
Let's do another example of that one real quick. Let's say that I'm gonna guess. I think the size of a full sheet is approximately, let's say 3 meters by 2 meters. That's probably a little bit off, but let's call it 3 meters by 2 meters. Area equals length times width. Area equals 3 meters by 2 meters. Area equals 6 square meters. Let's find out how many square feet that is. Let's make it a little bit easier on ourselves. Let's find out how many. Yes, we can do feet. 6 square meters. I'm going to go from meters to feet, but I'm going to do it a second time. Why? The orange is not showing up super good, sorry. Area equals length times width. Area equals 3 meters by 2 meters. I'm sure that's not exactly right. Don't have me. It might be rounded, though. 6 square meters. If 6 square meters, we're going to feet. Why do I have to do it a second time here? Yeah, because it's meters squared. It's not just meters. Can I use 3.28 feet as 1 meter in this case? Why? You're right, yes, but why? Because there's only one significant figure here. This quantity has 3 significant figures, and we can only use the quantity. We take the quantity that has the lowest number of significant figures. Since my given only had 1, it's fine to use this because now my found will only have 1. So I don't care about using this one that has 3. What is the answer? So mathematically, 6 times 3.28 times 3.28 equals, look here, my meters are going to drop out. I'm going to be left with feet times feet, which is square feet. Someone better do the math because I don't have my calculator. In fact, two someones better do the math.
Can't you do 3.28 squared times 6?
Mm-hmm. Yeah, you definitely could. That's not how I would find it to be easiest. That's not how I would do it. But that would be sound mathematically, certainly. Answer?
64.5504 squared. 64.
So what do we actually have to do? He said 64.550. No, Peyton, remain seated. 64.554. What is that with one significant figure?
65.
No. No. It's just 60. So 60 square feet. Do you corroborate? Does anyone have the same answer? You got the same one? Okay. 60. It was 64 point whatever you said. What was it? 64?
64.55.
Oh, so that actually should be rounded up. So we really need to have it be 70. Because it was 64.5504.
That rounds up.
So this rounds up to 0.6. This rounds up to 65. 65 rounds up to 70. But look, we can only have one significant figure because we only had one significant figure in here. That leads us to our next thing, which is our talk of actual significant figures. You've already got a kind of a hint of this. What is a significant figure? What is a significant other? Oh, that's the end. More on that next time.